Good morning. All right. So we're working with DC circuits and capacitors. We're starting with capacitors, and we will hopefully get into current and resistors today. Let's see where we end up. Last time we did a simple circuit with a few capacitors. We figured out that we can reduce those capacitors all the way down to one equivalent capacitor, figure out what the charge and the voltage and all that stuff are, and then work backwards and eventually get the charge, the delta V, on every capacitor in the circuit. And so we're going to start off with one of those. Okay, but we'll make it a little more interesting. We'll have 5 capacitors here. 6-volt battery. 4 farad. Of course, normally these would be like microfarads, but that's okay. We're just doing some quick calculations here. Let's make it a little simpler. And we'll call this 1, 2, and 3. And so that means that 5 is going to be over here. So we'll just call these capacitor 1, 2, 3, 4, and 5, and we'll give them the capacitance of 1, 2, 3, 4, and 5. And so we're looking for delta V 1, 2, 3, 4, and 5, and Q 1, 2, 3, 4, and 5, right? Q1, Q2, Q3, Q4, Q5. So go for it. Find the delta V on every one of these capacitors and the charge on every one of these capacitors. So you should be reducing this down to one equivalent capacitor. And as you look at these circuits more and more, you're going to start to spot things that resistors that are in series, resistors in parallel. Here you should see right off the bat that we have 3 here that are in parallel. I'll call that C equivalent 1. So I can redraw this circuit, right? Hopefully you're one step ahead of me. Haven't done anything with the 4 or the 5 yet. But I've changed those 3 into one equivalent capacitor. So now these are in series, right? It's hard to get numbers that work out real nicely for everything when you have combinations of series and parallel. You can make one set nice, but the other set doesn't always turn out nicely. Anyway, 1.62. So now we've got it down to one equivalent capacitor. Here's our 6-volt battery. And now we work backwards through the circuit. So we know this is not really one capacitor here. It's really 3 in series, right? So we're going to take a step backwards. And really that one of those isn't even a capacitor. It's 3 in parallel, but we'll worry about that next, one step back at a time. So we're going to go back to our previous circuit. That's a 4. Our C equivalent 1. What was that? 6, yeah. That's a 5. And we know there's a total charge stored of 9.73 in this C equivalent 2. But C equivalent 2 is really 3 capacitors in series. So that means that every one of the capacitors in series has the same charge and it's equal to the total charge stored by the system of all 3 of them in series. So Q4 equals what am I calling it? 6 equals Q5 equals Q total equals, I'm running out of room, 9.73 coulombs. That's a Q, not a 9. Okay. So if we know the charge stored on each capacitor and we know the capacitance, we can find delta V for each one. Okay, we're not done yet. So C6 is not really one capacitor, it's really 3 in parallel. So we need to work back one step. So what we want to know is, what is this voltage here? And that is just V6, right? The voltage difference between points A and point B, that's just V6. And that's really not one capacitor, that's really 3 in parallel. So I know the delta V for each of these 3 resistors. They're in parallel, and it equals VAB. So I say delta V1 is delta V2 is delta V3, delta VAB, or 6, whatever you want to call it. I'll call it 6, I guess, here. And what is it? 1.62. And if we know C and we know delta V, we can find Q on every one of these capacitors. And they're all going to be different. But what do we know about them? They're going to add up to be whatever was on Q equivalent. So 9.73. Okay. So I think you can see that this is a powerful technique. And it doesn't just work with capacitors. You can do the same thing with resistors. If I gave you a complicated circuit of resistors, most of the time, you can reduce it down, not always, but most of the time, you can reduce it down to one equivalent resistor. In this case, we're doing capacitors, right? But we can get it down to one equivalent capacitor and then work backwards one step at a time, figure out Q and delta V for every capacitor. The same thing with resistors, a complicated circuit of resistors, reduce it down to one equivalent resistor, and then work backwards and figure out delta V and the current I through every resistor. Doesn't work for every circuit, but we will learn how to deal with those circuits also. Okay, there's energy stored in that capacitor, right? That's what we've talked about. Because we separate those charges, and it takes energy to move the negatives away from the positive charges and put them with other negatives on the opposite plate, right? It takes energy to do that, and that energy is stored in the system. And then we can get that energy back out. We can run those charges through a light bulb or some other device and get that energy back out. So how do we know how much energy is stored in there? For a capacitor, it's going to be Q squared over 2C, or 1/2 Q delta V, or 1/2 C V squared. And we can use that. Once you know one of these, you can very quickly get the other two forms, because this is for any capacitor. And we can do that since Q is equal to CV, right? So once you know one of these forms, 1/2 CV squared, then you can get the other two by substituting in Q equals CV. So you might wonder where the 1/2 comes from, right? Because what is work? Work is Q delta V, right? We just finished that chapter. Work is Q delta V. We can move a charge through a potential difference, and it takes this much work to do it, right? Work equals Q delta V. Now, what do we have here? We have 1/2 Q delta V. You might wonder why there's a 1/2 there. Well, the reason is that if we just use the maximum delta V, we're not moving all the charges through that maximum delta V, remember. We're moving the first charge. The first charge, it doesn't take any work at all to move it. It's easy. There's no electrons over there repelling it. We pull an electron off this side, stick it on that side. It doesn't take any work at all. But the second electron takes a tiny bit of work, right? Because when I pull the electron off the positive plate, it's attracted to the plus that's left behind there. And then when I go to stick it onto the negative plate, there's already one negative there, so they repel each other. So I have to do a tiny bit of work pushing that second electron onto that plate. Then the third electron, I have to do a little bit more work, because now there's 2 electrons repelling it when I try to push it onto the plate. And the fourth one, I have to do even more work, right? And the last one, how much work do I have to do? The last one, I have to do Q delta V, the actual potential difference times the charge that's being moved. So the work done, right, it starts out with 0, and it ends up going to Q delta V, the total charge times the total potential. And what's the average of that? If it's a linear graph, 1/2. Okay, so that's where the 1/2 comes from. The work done changes as we move charges across. And so when you average it out, you get that 1/2 factor. All right, so one other thing we do with capacitors, we often put some kind of an electrical insulator between the plates. Right now, we've only been talking about capacitors that had basically a vacuum between the plates, right? Nothing that could conduct, and no insulating material. But that's not usually practical. Usually, they take some kind of an electrical insulator. So you have a conductive sheet. You have a conductive sheet, and you have an insulator, and you have another conductive sheet, and you slap them together like that. And then you have a nice parallel plate capacitor. The two sheets are conductive sheets are separated because you have this this insulating sheet in between, right? And often when you look at capacitors, they have a cylindrical shape to them, right? They look kind of like a cylinder. Why do they look like a cylinder? Even parallel plate capacitors look like cylinders a lot of times. And the reason is you want lots of surface area. So what do they do when they make the capacitor? They get a big old piece of foil that's going to be your conductor, and you put an insulator, electrical insulator on top of it. And then you take another big old sheet of foil and put it on top. And you don't want to have a big capacitor that's really big to plug into your circuit board. You want a tiny one. So they take it and they roll it up. And slide it into a cylindrical package. And now you have a ton of surface area, right? It's still a parallel plate capacitor, lots of surface area, and a big metal conductor, lots of areas, and in a relatively small package because you can manufacture it that way. Roll it up, stick in a little cylindrical pouch, and now you have a little capacitor you can plug into your circuit board. So, dielectrics. Dielectric is just a fancy word for electrical insulator. So, our capacitor up till now, we've just had our two metal plates. We're going to slide some kind of a dielectric material, an electrically insulating material in between those plates, fill the space between them with our dielectric. And it changes things a little bit. What happens is we charge up our capacitor. We get our positives on one side. Our negatives on the other. That creates an electric field. I'm going to draw my electric field separately over here. Here are my plates. And now we've got an electric field due to these charges. I'm going to call it E plates, due to the plates that make up the capacitor, okay? But the insulator the charges in the insulator are affected by this electric field. Now they can't move. It's an insulator, right? The electrons can't leave the atom that they're attached to. But what can they do? The electron cloud around the atom can shift a little bit, right? Remember, we can rub a balloon against our hair and stick it to a wall that's an electrical insulator, because the electron cloud around the atoms shifts a little bit due to that electric field. The electrons can't move very far, but they can shift a tiny bit. And that's what happens here. So if we zoom in with our microscope at the atomic level, we've got an atom here that has a shift. The electron cloud shifts a little bit. That's one atom. The electron cloud shifts a little bit due to this electric field that's set up. And the atom next to it does the same thing. And next to it does the same thing, and next to it does the same thing. We'll make it 4 atoms across. Okay? And so this happens throughout the whole dielectric. I'm just going to draw 2 rows here, but you get the idea. Now, what happens is all the stuff inside kind of cancels out. All of this stuff, all of this stuff basically cancels out. And what are we left with? Some positives on one face of the dielectric and some negatives on the other face of the dielectric. And they create an electric field in the opposite direction. They create an electric field this way. Call that E dielectric. It's not as big as the other field, right? It's a little smaller. So this one, I'll draw this one a little bit longer, and this one a little bit shorter, something like that. So when we add these two together, it's less than the original electric field due to the plates. What does that mean? It means our little battery can push some more charges across now, right? If we've reduced the electric field between the plates, it means it doesn't take as much work to move some charges. So our battery now says, hey, I can push a few more charges over there, and our capacitor can hold more charge. It's as if we've increased the capacitance of the capacitor. So our formula for capacitance has to take this into account. Now we have to add a term. So before, what did we have? We had capacitance was the area of the plates times our constant epsilon naught over the distance between the plates. That was our formula before. And we have to add one more factor here. We're going to add a kappa. That kappa is the dielectric constant. And kappa is greater than or equal to 1. So if it's a vacuum between the plates, kappa is 1. The dielectric constant is 1. Air is actually very close to 1. So really we could use air and vacuum almost interchangeably. And other materials, it increases from there. And for any capacitor, the capacitance with the dielectric is kappa times the capacitance without the dielectric. Maybe I should say that's if it completely, this is if the dielectric completely fills the space. Between the plates. All right. As I said, most capacitors have some kind of a dielectric in there. For the main reason is it makes it easier to manufacture them, right? You don't want those two plates to have any electrical connection between them. And you want them, you've got lots of surface area, you've got them close together, you don't want them to touch. Well, what's one way to guarantee they're not going to electrically touch? You put some kind of a barrier between them, right? So it's the easiest way to manufacture something is to put that barrier in there, the electrical insulating barrier, and then you put your plates together and then you've got a nice capacitor. So for a manufacturing process, I think you can understand it makes a lot of sense to have a dielectric in there. It also increases the capacitance. Now, most capacitors have some kind of a rating on them in terms of how much voltage you can apply to them. Why is that? Because this dielectric, at some point, if the voltage gets too high, the electric field gets so strong, the electrons can get ripped off the atoms that they're associated with, and they will move from one plate to the other, and you get an arc, a spark between the plates, and your dielectric has broken down. We say the dielectric breaks down, and it becomes a conductor for a moment. So that's like a lightning bolt or a spark, right? When you rub your feet against the carpet as you're walking across the room and you reach out to touch the doorknob and you get a little spark, the air has broken down. The air is a pretty good dielectric, right? It breaks down. The electric field is so strong, the air molecules, the electrons are being pulled in one direction by the electric field, but the positive nucleus of those molecules is being pulled in the opposite direction by the electric field. And if the electric field is strong enough, it will ionize the atom, it will rip the electron off, and the electron can move, and that's what you see, that's what that spark is, that's what lightning is. And when that happens, that's bad. It's not a capacitor anymore, right? You've just lost your capacitor. Your capacitor is not supposed to have an electrical connection between the plates. So if the dielectric breaks down, then you've ruined your capacitor. So that's why they have a voltage rating on them. Okay, so if the capacitor, if the dielectric does not completely fill the space between the plates, we can sort of play this trick and figure out what the capacitance is. So if we have parallel plate capacitors, We know that C is kappa A epsilon naught over the spacing between the plates. And let's say we had a capacitor and we only wanted to fill half the volume. With a dielectric. What do you think? How are we going to figure out the new capacitance? I'm not sure what the question is. Any insulator should be able to use as a dielectric. Some capacitors have liquid as the dielectric. Oil, some kind of oil or something. So they take their plates and they just submerge them into some kind of an oil mixture that acts as a dielectric, and it increases the dielectric constant. But typically they're solids. Oh, I believe so. I believe if the electric field becomes strong enough, any insulator will break down. You can. I'm sure there's a table in the textbook where it lists the breakdown voltage. That's how you know when you have like a Van de Graaff generator. We have some in our stock room we use sometimes. they charge up. They create a very, very high potential. I think we can get maybe up to 100,000 volts with our big one. Well, how do you know the potential? You hold another grounded conductor up next to it and you bring it close until you get a spark that forms. And when you get the spark that forms, you measure the distance and you know that that air breaks down, I forgot what it is, 10,000 volts per centimeter roughly. So as soon as you have a potential difference of 10,000 volts over 1 centimeter, your air breaks down and becomes a conductor. So if you have an 8 centimeter gap, if you're getting a spark across 8 centimeters, you know it's 80,000 volts, something like that. I forgot the exact numbers. Okay, our dielectric here. What we can do, maybe you've already sort of visualized this, we can cut this right down the middle and treat it like 2 capacitors. And what would they be? How would they be hooked up? In parallel. So we cut this right down the middle. I didn't want to do that. Cut it right down the middle, hook these 2 up together, hook these 2 up together. This one has our kappa in there, dielectric constant. That's not a very good. Okay. And so now what's our plate area? Our plate area here is A naught over 2, and over here it's A naught over 2. Our spacing is still the same. That hasn't changed, right? And so we could call this C1, and we could call this one C2, and we have the total capacitance is going to be, they're in parallel, right? C1 plus C2. And what is C1? C1 is kappa epsilon naught times the area, which is A over 2, over the distance. And C2 doesn't have the kappa. Everything else is the same. And we add them up, and what do we get? Kappa C naught over 2 plus half the original And you can do the same thing if I hooked it up the other way. We have a capacitor here. Yeah, I'll just call it D. And we fill half the volume with a dielectric, but we do it in this orientation now. This looks like two capacitors in series, where this is D over 2, and that's D over 2. And this one has a dielectric in there, and the other one doesn't. Plate area is the same as it was before, and you can go through and do the math and figure out what that looks like. Okay, we ready to talk about current? Okay, we know that something moves, right? There's two types of charge, positive and negative, and we know something moves. Somebody guessed, the story is Ben Franklin guessed, it was the positive charges that moved. So all of our current, the convention for current flow is the flow of positive charges through our circuits. We figured out later on that that's not what happens. It's the negatives that are moving. And how do we know it's the negatives that are moving? Well, a couple of clever experiments. The first one has to do with the fact that electrons are actually particles with mass. So they have inertia. And maybe you've done this yourself when you were a kid. You had a wagon and you had a ball in the wagon. And you gave the wagon some acceleration in this direction. What happens to the ball? It ends up at the back of the wagon, right? It has inertia, it resists that change in motion. The wagon moves forward underneath it, and the ball ends up back here, right? So what they did is they took a conductor. They knew the charges were free to move in the conductor. Whatever charges moved, they didn't know which ones. Charges were free to move in there. And they figured these are charges, these are particles with mass. They have some inertia. So if we take a conductor, piece of metal, and we accelerate it, then the particles that are free to move, like the ball in the wagon are going to lag behind. So if positive charges are free to move, we'd get positive charges back here and negatives over here. We can measure a potential difference and see which ones we get. And if negative charges move, we'll get negatives lagging behind, right? And it turns out, of course, this is what was observed. So that was the first, well, I'm not sure the timing here. That was one way that we demonstrated that the negatives of what's moving. Another way to demonstrate it that was done, it may have been around the same time. Temperature tells us how much the atoms and molecules are vibrating that make up a substance. So all substances that are above absolute zero, the atoms and molecules are moving, they're vibrating. Temperature tells us how much they're vibrating. And as you cool something down, the atoms and molecules vibrate less and less and less. And that's why we have something called absolute zero, because at some point, the atoms and molecules stop moving. And then you can't make them any colder, right? There's not less motion than nothing, right? So as they vibrate, that tells us the temperature. The hotter the object is, the more they vibrate. The colder it is, the less they vibrate. And the reason we have a cutoff at the end, absolute zero, is that you can't make something vibrate less than nothing, right? As soon as the atoms and molecules stop vibrating, it's at absolute zero. Of course, you can't ever make it that cold, but there is a limit. So if you can heat something up and get the atoms and molecules to vibrate more and more, and something in that substance is free to move around, it's going to move faster and faster and faster as you heat it up. And eventually you can heat it up so much, like boiling water, right? What happens when you boil water? You heat it up and the water molecules start moving faster and faster. And pretty soon they're moving so fast, they can't hold on to each other. And some have enough energy to break free and become gas molecules. They can leave the water. They have enough energy, they can break free and leave. And they've boiled off the water, right? You can do that with a solid. Take a piece of metal, if you heat it up high enough, eventually something is going to leave that surface. What is it? It turns out it's electrons. Electrons get moving faster and faster as you heat it up, and they get enough energy that they can break free from the bonds that hold them to the surface and leave. You can literally boil electrons off the surface of a metal conductor if you heat it up high enough. And so that was another way to know that the electrons are what's moving, because that's what comes off when you heat it up. Which one? These are just side anecdotes to tell you that how we figured, because you probably were wondering, how did we figure out which charges were moving in the circuit, the electrons or the protons? So I was just trying to shed some light on these. If an object is free to move and it has mass, it has inertia, and you accelerates something forward, it will lag behind. Okay, it's like hanging a weight in your car. The car accelerates forward. What happens to the weight? It lags behind, and the angle in the string will cause it to move forward, right? So it doesn't matter that one's lighter than the other. What matters is that they all have inertia. The one that ends up at the back side of what's moving forward is the one that's free to move. I guess
Yeah,
if the, go ahead.
But how could you tell the charge that got left behind is positive or negative?
No, you could just measure the potential difference. You could put a voltmeter here. That would tell you which side's at higher potential, right?
Oh, that's cool. Thank you.
Okay. I guess if both charges were moving, then the mass would matter, right? If they were both moving, the mass would matter. Luckily, that's not the case. That would complicate things. Okay. All right, so what happens when we, most textbooks have a long derivation of current. I don't think it's necessary, as long as you kind of understand conceptually what's happening. So if we have a wire here, we've got electrons that are free to move. We set up an electric field. The electric field gets set up in the wire. And that causes the, I'm going to make my electric field go the other way, sorry. The electric field causes the electrons to go in the opposite direction. So this electron starts moving, and it moves until it collides with something, an atom that makes up the metal wire, right? And then what happens? It bounces back a little bit. And then it starts moving again. And then it collides with something, and then it bounces back, right? And then it starts moving again, and then it bounces back, and then it starts moving again. And it has this chaotic motion. But overall, the average motion is opposite the electric field. And we say that this is the drift speed of the electrons. It's some kind of average velocity that they're moving in the metal conductive wire. And that's why we have resistance in wires. The electrons, they start to move, and then they encounter an obstacle that prevents them from moving. They have to start moving again, and then they collide with something. If we could eliminate those collisions, we would eliminate resistance in wires, and we can do that. We have these something called superconductors where there's no resistance. But most of our conductors, there's this motion that's interrupted by collisions with the atoms and molecules that make up the wire itself. So V drift is a small number. It takes about 90 minutes for an electron to go 1 meter in your normal household wires. 90 minutes to go about 1 meter. So how come the light turns on right away when you turn the switch on? Because the wires are full of electrons, right? It's like a hose. If a hose is empty and you turn the faucet on, it takes a long time before the water comes out the other end. But if the hose is full of water and you turn the faucet on, as soon as some water moves in, some water is pushed out the other end, right? Because the hose is already filled with water, it all starts moving at the same time. That's what happens with the wires. The electric field moves at the speed of light, right? The electric field moves very quickly through the wires, propagates quickly, and all the electrons in the wire start to move at the same time. Okay, good. Now, this also might help you picture why resistors heat up. The electron starts to move and it bangs into something, an atom or molecule that makes up the resistor. And then it starts to move again and it bangs into another one. Well, what happens every time it bangs into an atom or molecule? It gives a little bit of energy to that atom or molecule. Now that atom or molecule has more energy, it starts to wiggle more, it starts to vibrate more. Well, what does that mean? That means it's at a higher temperature. So you can see why you run current through a metal conductor and it starts to heat up. In fact, that's how old-fashioned incandescent light bulbs work. You run a current through the light bulb and it gets so hot it starts to glow, and it glows white hot. That's not very efficient. They're actually very efficient heaters. They heat up a lot, and most of the energy you're putting in is going into creating heat. Very small percentage of it is going into light. So they're pretty efficient heaters. But if you want a light source, you want the energy going into making light, not heat. And especially if it's summertime, you're putting energy into making light in your office building, and then you're putting more energy into air conditioning to get the heat out that you're creating when you make the light, right? It's a vicious cycle. So these more efficient light bulbs are really wonderful. And one way you can tell how efficient they are, you try to touch an incandescent light bulb that's been on for a little while, and you can't do it. They're hot, right? They're making a lot of heat. You try to touch an LED bulb that's been on for a while, yeah, no big deal. They're not hot. They're not creating much heat. Most of the energy is going into light. Okay. Oh, I went a little over there. Got carried away. Got excited. All right, let's take a 10-minute break. I've heard a rumor that there's going to be some kind of military flyby here that's happening like right now. So we'll take a 10-minute break, and I'm going to stick my head outside and see if there's any excitement out there. And then we'll come back in 10 minutes. All right, we're back. That was not as exciting as I thought it was going to be. Oh, the little things that excite us these days, huh? Okay, let's work through this sheet together. So we're going to talk about current. And it says the circuits at the right contain identical batteries, bulbs, and an unknown identical element labeled X. How do the bulbs compare in brightness? So one of them is hooked up before this unknown element, and the other one after. So first, let me tell you the brightness of a light bulb. What does that tell us? It tells us power being dissipated, how much energy is being dissipated per time, right? Power. So the power in a light bulb, where are we here? I need space. I'll sneak it in here, or maybe I'll sneak it in here. So the brightness of a light bulb is proportional to the power it's dissipating, the amount of energy it dissipates per time. And the power in a resistor is given by I times V. And since V equals IR, we could also write that as I squared R or V squared over R. So that's the power dissipated in a resistive device. Now, if the light bulbs are identical, that means the resistance is the same for all of them. Then, what does the brightness indicate? How much current is going through them, right? So we're going to utilize them as current, sort of a simple way to estimate the current going through different parts of our circuit by looking at the brightness, comparing the brightness of identical bulbs. Okay? So what do you think? We've got these two circuits hooked up. You put the bulb before whatever that thing is, a toaster or something else, right? Put the bulb before it. You put the bulb after it. How does the brightness of our bulb compare? How does the current compare in each case? Yeah, what do you think? Same brightness? So how does the current compare from the light bulb to the element X? The second part of this question. They have to be the same. Why? They are in series with each other, right? And when things are in series, they have to have the same current. There's no fork in the road, no branch for the current to take a different path. So the current has to be the same in both of these. So if the current is the same in both of these, then the battery doesn't care what order they're in, right? It sees a certain total resistance and it flows current appropriately. So if the current's the same in both and the battery doesn't care what order they're in, then they have to be the same. Both of these have to be the same. We okay with that? The point here is that current does not get used up as it goes through a circuit. Current is the flow of objects, right? Electrons, real things with mass. They don't just disappear when they go through something. Every electron that goes through one element in series has to go through the next element in series. They all move the same. They just come out with less energy. They go in with more energy than they come out with. Okay. Now, it says we replace element X with element Y. So everything else is the same. Batteries are the same. Light bulbs are the same. But X and Y are different. And it says the bulb on the left is brighter than the bulb on the right. What can we conclude about the resistance of element X compared to element Y? Okay, so we're getting more current in the circuit on the left, the circuit with the element X in it. So that means that the resistance has to be less over there because the batteries are the same. Okay. In each circuit, how does the current through the bulb compare to the current through the unknown element? Same, they are in series. Okay. And in each circuit, how does the current through the bulb compare to the current through the battery? Current through the bulb compared to the current through the battery. They are in series, right? Any current that comes out of the battery, where's it going to go? Through the light bulb. There's no other choice. So those currents have to be the same. All right. Okay, now we have these three circuits here. Predict the relative brightness of bulbs B1, B2, and B3. So here we have basically an X, right? Element X, element Y, element Z, right? We've got some unknown element, but they're letting us peek inside and see what they are now. And we want to know if we can peek inside and see what's inside these mystery boxes, can we predict which bulbs are going to be brightest here, 1, 2, or 3? What did we say up here? If the brightness of these two bulbs was different, what did that tell us about the resistance of X and Y? Now come down here where we want to compare the brightness of these bulbs. So what could we look at? What might tell us the brightness of those bulbs? The resistance of these unknown elements here, but here there are known. Okay, one more time. In this case, people seem to be okay with this one. We were comparing the brightness, right? One of these was brighter than the other. So because one was brighter than the other one, people agreed that element X had to have less resistance. We okay with that? So now they're telling us the resistance of the boxes, right? They're letting us see inside the boxes. So we should be able to know which one of these has the greatest resistance and which one has the least resistance, these boxes, right? We can see inside them. So if we know the resistance of these boxes, what can we say about the brightness of those bulbs? Okay, should we see? I'm not sure how well this is going to turn out. Let me see. If I stop sharing and I change this camera. Oops, what happened? What just happened? Okay, can you see? I don't know how well that's showing up.
Yes, we can see.
Okay, I got a circuit here. The power supply comes in this side. A light bulb. Can you see any of that? We can see it. Excellent. Okay, so for the first case, we've got a B1. Let's call this B1. And we're going to compare B1 and B2. So this is B1 and B2. Okay, you ready? We can see those. So all you care about is this one. This is the mystery box here. So there's one light bulb in our mystery box. That's case 1, and this is B1. And now I'm going to put 2 light bulbs in parallel in our mystery box, and we'll compare. This is going to be B2. You ready? So B1 and B2. B1, B2. Which one's brighter? 2. Is that right? So now we need to compare, what do we need to compare? 1 and 3. 1 and 3. So now we'll look at this bulb. Okay, so this is bulb 1. This is our mystery box down here. This is bulb 1. And now it's bulb 3. This is our mystery box, 2 in series in our mystery box. And this is bulb 3. So 1, 3. 1, 3. We good with that? So in this case, what's the resistance here? R is equal to, if each one of these light bulbs has a resistance R, so let's start with B1 here. This has a resistance R. What would be the resistance of this box? We have two of them in series. For what do we do for resistance? You had a whole lab on this, or maybe two labs by now. This has a resistance of 2R, this box, right? And this box in the middle has a resistance of R over 2. Okay, so up here, remember, up here we said if this bulb was brighter, this resistance had to be less than the other one. So down here, we're just turning it around a little bit. We're saying, we know the resistance in the boxes, so tell me which one's going to be brighter. Well, whichever one has the smallest resistance has to be the brightest, right? That's what we concluded up here. So the brightest has to be B2, followed by B1, followed by B3. Is that right? B3. 2, 1, 3. And that's what we saw, correct? Okay. Let's keep going. You have two in parallel, two resistors in parallel. We haven't covered it yet in lecture, but you had a whole lab or two on parallel resistors, right? We'll go over it again in lecture. Okay, potential difference. So now we've got a light bulb. Here's a single light bulb and a battery. And so what's the potential across the bulb? It's V battery, right? I'll just say V battery. Or maybe I'll put it. Okay. Then it says we've got these two bulbs, 1 and 2. The current. How do the currents all rank? Bulb 1, bulb 2, and bulb single. That's this one. How about 1 and 2? How do they compare? And let's put, how about this? How about we put a number here? This is a 6-volt battery. If that's 6 volts, then what's this one have to be? 6 volts, right? That's better. Put some numbers in there. That way it's more obvious what we're trying to say. Okay, so we're down here. How does the current through 1 compare to the current through 2? They are the same. They are in series with each other. The current has to be the same through both of those. And how does that compare to the current in that single circuit with the single light bulb? it's going to be half as much, right? Because there's twice the resistance here compared to this resistance. So the current, if this is the same 6-volt battery, then the current is going to be half of the one that happened up above there. And how do the voltages compare? V battery, V bulb 1, V bulb 2. If these two have the same resistance, then they're going to split the voltage equally, right? Because they both have the same current, right? We know they both have the same current. And what else do we know? V equals IR for a resistor. So if they both have the same current and they both have the same resistance, then the voltage has to be the same. So it has to be half of, there's two of them, it has to be half of the 6-volt battery. Okay. Where are we? The batteries are the same. We said their batteries were the same, right? I think I just gave you that information. Now it says rank the potential differences across bulbs 1, 2, and the single bulb circuit. Well, we already listed them all here. I think we're done with that, right? The single bulb is the greatest, right? It's 6 volts. And V1 and V2 are the same, and they are 3 volts, right? Okay. How does the potential difference ranking compared to the brightness ranking? Oh, okay. They're trying to show that the potential difference is the same. So let's go back up to our power. So remember, the brightness of these bulbs is proportional to power. But if we are using identical bulbs and we know that they have the same resistance, then if one is brighter than the other, then that means that it has a greater delta V across it, or it has a greater current through it. Either way, it tells us the same thing, right? More current or more delta V gives us brighter bulbs. Okay, that's what they're trying to get at here. All right, let's move on. What does this say? Predict what the voltmeter would read if it was connected to measure the potential difference across the network of 1 and 2 together. So we're going to hook up our voltmeter here. What's it going to read? Six volts. Okay. So those were in series. Now we're going to do the same thought exercises for bulbs in parallel. Maybe I should set up a PhET simulation. Should I do that real quick? Let me see. No, actually, I don't want that. Do I want that? I want this. And we want electricity. Okay, so let's go back and do this real quickly. Share. There we go. Okay, so what did we do? We had a battery. We wanted it to be 6. Oops. Let's make it 6. Oops. 6 volts. We had 2 light bulb. Well, there, I guess they were light bulbs, weren't they? I don't think I'll be able to make that. Oh, maybe. What did I want it to be? Okay, so let's take a look at what we've got here. We've got a circuit. And this one comes over here. And then this one comes over here. This one closes it off. Okay, we had 2 in series, same brightness. And when we measured the potential across this guy, we got 6 volts. When we measured the potential over here, we got 3 volts. When we measured the potential over here, where am I? We got 3 volts, right? And when we measured the potential across the whole thing, we got 6 volts, the same as the battery. Okay. What else did we say? Oh, we wanted to know if the current was the same through both of them, right? So we can split. What do we want to do? Let's put a current meter here. It's measuring the current. And let's put another one over here. Let's put another one over here. Where do we want to put it? Here. Okay, we convinced the current is the same through everything in series. And the voltages of these 2 things in series add up to be the battery. We good with this one? Okay, so let's go back to our sheet. Share. And now let's do it for parallel. So the question is, rank the currents through bulbs 1 and 2 and the bulb in the single circuit above. So the single circuit was this one. Okay, single. And now we have two in parallel. So current, we're ranking current through 1 and 2. How do the currents compare between bulbs 1 and 2? One and 2 have to be the same because the R's are the same and the V's are the same. We know the V's are the same because they're in parallel. And if they're identical, the R's are also the same. So that means that the current has to be the same, right? So I1 equals I2. And how does that compare to I single? Equal. Okay. Because what is the voltage here? This is 6 volts. This is 6 volts. So for I1, what do we have? It's going to be 6 volts over R, right? And what do we have for I single? 6 volts over R. If the R's are the same, the currents have to be the same. Now it says, how does the current through bulb 1 compare to the current through the battery? So we have current through the battery. We have current through 1. And we have current through 2, right? I1 plus I2 is equal to I battery, right? So half as much for I1 as for the battery, okay? The current splits. And because the R's are equal, it's half and half. Okay, now it's asking for potential differences across each element. If the battery is 6 volts, let's just make this 6 volts here. How much do we have across bulb 1? Yes. How much do we have across bulb 2? Yes. It's the same everywhere. They are in parallel. They all have the same voltage. How does the potential difference across the battery circuit compare to the potential? They are the same, right? The potential difference is the same in the single as it is in the 2 light bulb circuit. Potential difference across bulbs 1, 2, didn't we already do that? They're all the same, right? And we know that they're going to be the same. Okay, so let's take a look at our circuit. Share. Okay, go away. Oops, didn't want that. 6 volts. We've got a light bulb. What did I make? I made them all, so why did I make them 6? And we have another light bulb, and they are in, oops. They are going to be in parallel. Okay, and we've got a circuit. Goes in there, comes out here, comes out here. Okay, so this is our circuit, right? The brightness is the same. Let's measure voltages. The battery voltage is 6. And if we move this over to this, it's 6. And if we move this over here, it's 6. In fact, I could touch this wire anywhere. This is an equipotential surface, right? Anywhere here. This is all going to be 0 on this side if I'm calling this 0. And this is all going to be 6 volts higher. Okay. And if I want to measure current, let's break a couple of these. This is the current coming out of the battery. And we want to know the current going into, coming out of this bulb here. So we'll break this one. We've got current going through that bulb. And we break this one, and we've got current going through this bulb. Okay. You see how quick and easy this is? I love these simulators for DC circuits because you're solving a problem in the book. There's no answer. In 30 seconds, you could whip it up here and check your answer and kind of get a visual of what's going on. So play with these a little bit. I think they're really useful. Okay, we'll pick it up next time. Or I'll tell you what I'll do. I'm going to post this. I'll post this with, we've got one more sheet here. Go through it before next class so we can go through it kind of quickly in the next class. Okay? So I'll post there's one more work that we're going to finish. We ended here today, right? So check all of this, look over before the next class. Okay, and then we can go through it a little faster that way. Okay, some of you I will see in lab. The lab video is posted, so we'll just be going over that today. If you want to watch the video instead at your convenience, you can do that. Otherwise, I'll see you in lab. Have a good afternoon.